Okay, our discussion of sampling distributions continues in section 8.2. So now we're going to see what happens when you sample from a population that's successes and failures, and you count the number of successes, but you then average the number of successes in the observations you take. So that says maybe you sample 10 values from a population that contains a proportion P of 0.2 of defective items and compute the proportion of defectives in the sample. So on average, now we're getting proportion, right? So if you found 2 defectives, you divide it by 10 and get 0.2 for the sample proportion. So the sample proportion is always between 0 and 1 because it's a number of something you found in the sample divided by the sample size. So it's in proportion. So these numbers down here, they're not how many defectives, they're the fraction of the sample that's defective. And you would imagine that 0.2 would be a popular value because that's the probability of defective items. You'll notice it's a little bit skewed to the right. Single peak skewed to the right type of distribution. And then it's discrete in nature because you can only get certain values if you count 10 and you ask how many are defective and then you compute the proportion that are defective. You can only get 0, 0.1, 0.2, 0.3 up to every 10th because that's your sample size is only 10. So it's discrete, it's skewed to the right, single peaked, but it's nice looking, it's a distribution. And then down here we say, since the sample proportion is just a binomial quantity, so the actual number of successes would have been binomial with n is 10 and p is 0.2. Dividing by n then divides the mean by n. That kind of makes sense. So if the mean was 2, when you count how many, when you take the count and divide it by 10, the average value is going to be the average you had before divided by 10. So for proportions, the mean for the sample proportion is the population proportion. So that makes sense. And then the standard deviation, which measures the spread. If you divide all the values by n, it divides the spread by n. So the standard deviation gets divided by n. And if you do the math, it looks like this. So we have, for binomial, the mean is NP. For proportions, the mean is P. For binomial, the mean is this NP1 minus P. Sorry, the standard deviation. And then for proportions, the standard deviation is square root of P1 minus P divided by N. So those are just things that we'll be using over and over again. Okay, making headway. So let's compute these in our example. Really, our example was N is 10 and P is 0.2. So up here, it's just 0.2, no computing really necessary. And then that there, what's it look like? P is 0.2, so I gotta be careful how I do this. So I'm gonna go, I'll try doing the square root guy. Second square root, then I'll take 0.2 times 0.8 divided by 10, like that. So that's P times 1 minus P. So 1 minus 0.2 is 0.8. Divide that by 10, take the square root, off we go. 1, 2, 6, 5. I'll put that rounding. 1, 2, 6, 5, like that. It says here, NP times 1 minus P is less than 10. So here we go again. We can use the same NP 1 minus P because if the binomial quantity was normally distributed, dividing by n to get the sample proportion, it just changes the position of that normal distribution. The shape will stay normal. So it says here, since it's less than 10, we can't use the mean and standard deviation to do anything. We would have to convert any questions we have about the sample proportion into questions about binomial distributions and either look it up in tables or compute the probabilities and add them up by hand, or use a calculator that can do sums of binomial probabilities. But that's not really the job of this class. The job of this class is to think about things where we have reasonable size samples. So let's look at cases where a normal approximation can be used. That is when NP 1 minus P is at least 10. And we'll see how you can use the normal distribution to talk about the sampling distribution of the sample proportion when the sample size is large enough, and find out that it's normal and we have its mean and standard deviation, so we can do stuff with it, because we'll be needing to do that shortly. Okay, so how are we going to do this? We'll say the sample proportion has an approximate normal distribution if n times 1 minus np times 1 minus p is at least 10. We'll say the sample proportion has mean p, we know that, and standard deviation that way, square root of p 1 minus p over n. And so then if we know it's a normally distributed situation, we can use z values and use them to find probabilities. And here we go. Let's compute the approximate probability that if 2% of cell phones have defective batteries, a sample of 1,000 cell phones has more than 2.5% defective batteries. So we'll check the NP 1 minus P thing. So N is 1,000. I'll be sad if it doesn't work. P is 0.02, like that. And 1 minus P is 0.98. And so we'll go 1,000. I'll get this out of the way. 1,000. I'm looking. 1,000 times 0.02 times 0.98. 19.6. NP 1 minus P, 19.6. Yay. P hat is approximately normal. Okay, and so that means we can compute z values. Okay, so for the mean of p hat, write it that way, is 0.02. And sigma for p hat, I've got to compute this thing here. For the mean, I just read it off because it's p. For sigma, I have to do stuff. Okay, so I'm going to do second square root 0.02 times 0.98 divided by 1,000. So our sample size is 1,000. And you notice our test number isn't that much bigger than 10. So with smaller sample sizes, you're just doomed to not be able to use a normal distribution, especially if the percent is small, because it enters into here, right here, and shrinks this thing down. So I got 0.0443. I'll write that. It's pretty tiny. It's 0.5%. That kind of makes sense. Okay. 0.00443, like that. Okay. And then all I have to do is compute some z's. So I'm going to compute, I just need it for this, for 2.5%. So I'll write it here. Z for 0.025, which is 2.5%, is, so you take a p hat minus p over this thing here, p 1 minus p over n. So that's value minus mean over standard deviation. So we get 0.025 minus 0.02 over 0.00443, like that. Let's go ahead and do that. So I have to use parentheses. 0.025 minus 0.02 divided by 0.00443. I'm making a habit of looking at my calculator before I hit enter to make sure I've done something approximately right. Okay, here we go. We're going to be using tables, so I'll use 1.13. And then I'm heading over to the tables. The area in the normal tables So it's, what is it? 1.13, I'm here. 1.13, 8708. And then we're looking here, it says it's a more than question. So in the bell curve, that's supposed to be happening. So what are we thinking here? It's something like this. So we said that we have a normal distribution. The mean is 0.02. The standard deviation distance is 0.0443, like that. And then we found that 0.25 was about one standard deviation above the mean. So maybe it's here, 0.025. This is the picture of p hat itself. And then we looked in the tables and we found the chance of being less than, which is down here, is 8708. It says up here, what's the chance the probability is more than? So that'd be this side. So we have to take 8708, subtract it from 1. So our answer, our probability of a p hat exceeding 2.5%, or 0.025, which is what we computed, is 1 minus 0.8708. Okay, which ought to be 0.1292, but I always check that. 1 minus 0.8708. 1292. Yeah, we're in business. Okay, check. So that just goes to show you that as long as you can show that the proportion is a normal distribution, we can do business as usual. Let's keep going. It says here, just for our own peace of mind, here's a histogram of the situation. And here's what we needed to compute. All right, and now what's it going to tell me to do? Oh, now we can do it. Well, we jumped the gun, man. We beat him to the punch. What did we get? We got 0.1292. Right. So I just saw that big empty space where I could do work, and I did the work there and didn't go to the next page to have me led through the process because I already had everything I needed, and so did you. And that marks the end of this section, all in one go, unless something horrible happened. I'm hoping everything went well, and I'm going to stop recording.